Hello, UNIF 2020. This is David Cerna, and I'm presenting a work done together with Alexander Leitsch and Anela Lolic on the unification of term schema. So, if at any point there's a cut in this presentation, this is most likely to do with some outside environmental noise. Unfortunately, I'm recording at home. So if you hear a cut, that's what this is. And so as an outline for this presentation, I will start by giving some background, because if you look at our UNIF abstract, there's not much background information about why we're even doing this. And the paper that we have out there right now in arXiv is quite long, so I give a bit of succinct background information in this. If you want more details, you could go to the arXiv paper. And then I'll go over in more detail our examples and these concepts. So let's get started. So where did the motivation to actually study unification over term sequences start anyway? So it started from automated proof analysis in the presence of induction. So maybe some of you know this work by Matthias Botts, Alexander Leitsch, and a few other people concerning Fürstenberg's proof of the infinitude of primes, where using the series method, that's cut elimination by resolution, right? They were able to use to analyze this proof and show a relationship to Euclid's proof of the infinitude of primes. And here they didn't really have a schematic formalism. They had like a rudimentary schematic formalism, I say it here. All right. So it was really without a formal framework for schematic objects. Well, after this work, there are several attempts at actually putting a schematic framework together. The first one being Dunchev et al. This is worked together with Alexander Leitsch as well. There's a PhD student at the time, where the first schematic framework was given. Later on, you have this paper Leitsch et al. With work with Nicolas Peltier, where I will explain how this was put together with the calculus made by Nicolas Peltier. And then you have this work that we cite in our UNIF abstract that the three of us did together, where we tried to make a better framework than what already exists. So, some of you are probably wondering what we mean by schematic proofs and its relationship to induction. So I'll give a little bit of an outline on this slide. Not really a schematic calculus or any of the details, but just what a schematic proof is. So imagine we have this proof here, phi, and it has some free variables which could be instantiated by numerals. All right? So we have this instantiation at the bottom here. If we go through the tree and we follow some path through the tree, all right, we could see that we could get to these things which are called links. All right, and these links are connections to other proofs, where at those links we might have some other substitution. So this substitution was transformed into sigma prime and tau. All right, so there's an order relation between sigma and sigma prime, but there does not necessarily have to be an order relation between sigma and tau, because it might be the case that tau is pointing to a different proof. So you see sigma is keeping with the same, sigma prime goes to the same proof, just with a lower number, a lower instantiation, while we go to phi with just a completely different instantiation. So we're stepping to another symbol. So you might notice this is very similar to primitive recursion. All right, so we could allow these nested calls. We have restrictions on the references. For example, phi cannot be referenced in psi, because that would cause a kind of mutual recursion, and so on and so forth. There's going to be these things called the least proof, which is the least proof in the ordering. And when you get to phi base, right, we could say that at phi base there's no calls. They don't have to do any calls in this base case, similar to what you would have in certain primitive recursive function definitions. And this here altogether makes a proof schema. So a proof schema is really just a way of putting together different proof parts to make this inductive construction. All right. So now, for those not familiar with proof analysis, I go over a little bit about it, right? So if you look at what we have on this previous slide, this would be a formal proof, all right? So with enough effort, for example, the Fürstenberg proof required a lot of effort. With enough effort, you could actually formalize a mathematical proof in one of these logical calculi, right? This is probably not, it doesn't sound so special to most people in the audience, all right? So you could do this formalization in logical calculus such as Gensen sequent calculus, right? And this formalization will most likely result in a proof with cut formula rather than what we call an analytic proof, or a proof where the final statement is constructed from subformula that occur in the proof. So everything that occurs in the proof is a subformula of the final statement of the proof tree. All right. So what does a cut look like? So the cut rule is given here. See, in the antecedent of the sequent, we have a cut formula, and in the succedent, we have a cut formula. And then we could cancel those cut formulas out, and we get this formula delta prime, gamma prime. Putting the two what's left over together, right? So this action simulates Schemata, and it simulates the introduction of external theory into the proof, right? Analysis of proofs is completely concerned with the manipulation of this cut structure. Not necessarily the removal, just the manipulation. But in the case of removal of the cut structure, or what we call elimination of the cuts, you get an analytic proof. And such proofs provide additional mathematical understanding, like with the Furstenberg proof, how we now understood how that proof is connected to the Euclid proof. There's different types of cut elimination. So in the simplest type, the one introduced first, which was introduced by Gensen, is this local type of cut elimination, where the cut formula's complexity is decreased or the distance from the leaves of the proof is decreased. So we're moving the cuts up the proof and we're reducing their complexity. So this was used to prove consistency, using in consistency proofs, right? But it could also be expanded way beyond this intended scope. I'm not going to go over more detail about local, because what we really care about is global cut elimination, right? Where we put the cut formulas or the cut structure of the proof in an intermediate formalization. So we restructure this into something else. For example, the series method could be used to transform the cut structure into a negation normal form formula, which then can be refuted by resolution, right? So now maybe you're starting to see where the unification is going to come in here. All right, so we're taking this from proof analysis. We have this formal proof. We turn its cut structure into an NNF formula, and then we're refuting it by resolution. So we're getting there, all right? So now you might ask, why don't we use local cut elimination? Because, well, Gensen's paper is very important. It's a very old method, all right, and it seems to do the job. So now the problem is in the recursive setting, all right? If we have this kind of situation here, you see we have a cut and we have two proof links. All right, so these are the links to other proofs in this net of proofs that makes it the proof schema. All right, if the call structure is non-recursive, then the proof references can just be removed. Cool, so that's easy. But when you have recursion, right, you don't know how do you push the cut up, because that might be the same proof that you're working in now. So that means the cut should show up in the proof below as well. So this recursion kind of really messes up the concept of position in the proof, because there's no the position is dependent on the parameter instantiations. So in the case of recursive proofs, or this schematic proofs, right, the use of a global cut or the use of a global approach is really necessary, because then we just take the cut structure and remove it as a recursive negation normal form formula or an inductive definition. All right, so let's look at this global cut elimination. So you have this recursive NNF formula. You have the proof here with cuts. You look for the cut ancestors, so the formula that are used to construct the cut, right? And then you could start building up this formula here. So you see, this is the axioms. We either have A, not A, or not A or A for the different axioms, depending on red being it's part of the cut ancestors. All right. We ignore unary rules. All right. And when it's a binary rule, depending on its cut ancestry, we either put an and or. All right. What happens with proof references? Proof references become defined symbols which have recursive definitions attached to them. Right. So such a recursive formula is always unsatisfiable. Any instantiation of it's unsatisfiable. Right. But what we really want is for proof analysis, we need a finite representation of this refutation. We need to finitely represent what this thing is. All right, and this is where things get difficult, and where resolution calculus specifically built for this, as well as unification, became necessary. So I give a very complicated. This is actually given in the paper that we cite often in the abstract. This is an example of a formula which has an inductive definition extracted from a real proof, and one that we show can be refuted in a finite represented way in our calculus. I won't go over the details of what this actually means. I just want to show what it looks like when you extract this from a proof and what it is that we're getting in the end. We'll look over simpler examples. All right. So refuting recursive NNF formula. So how was it done in Leitsch et al. 2017? There, the N-clause calculus of Alvarantinos et al., also Nicolas Peltier, who's on both papers, was part of this work, was used to construct refutations. Right? It's completely automated. However, this calculus is extremely weak, and most mathematical problems of interest lie beyond it. For example, the one on the previous page cannot be refuted by this calculus. Right? In the more recent work, this one from 2019, we considered a semi-automated approach to dealing with this recursive NNF formula. Right? And what we did was we designed a resolution calculus which could be used by a person and is more like something that could be used interactively. All right? But this resolution calculus required a new theory of unification, which is still in work. This is not finished work. This is just the ideas that we outline here, all right, for schematic terms. And this is what we discuss in the rest of this talk. So we've talked a lot about schematic things, and this is about unification over a term schema, all right? So let's give a general idea of what this is. So it's nothing more than you have an infinite sequence of first order terms, where this n is actually part of the object language, this numeric parameter, and we want to talk about these infinite sequences which are finitely representable, only those infinite sequences. All right? So syntactically, what we're representing is we have this hat symbol here. We use hat to represent defined symbols. We just have some term which is constructed from defined symbols, and it may contain many defined symbols, not just one. It may contain nested ones. We go over this in a second. All right, and these are indexed by this numeric parameter n. All right, defined symbols, all right, also have associated in defining equations. You could think about this as you have with primitive recursion, where you have the equations defining the primitive recursion. All right, and this allows normalization of these terms. So normalization is done with respect to parameter assignment. So as you can see here, we have this is normalization at the bottom point. Normalization of the term with respect to the parameter assignment assigning n to alpha, where alpha is just some natural number. So this is actually a syntactic representation of a numeral. In this talk, I only use one parameter because it gets a bit confusing with multiple parameters. So if anyone's interested, yes, you could have as many parameters as you want. This is fully done in the paper on archive that we cite in the abstract. So what about substitutions, right? So substitutions, why not make them schematic too? Of course we do, right? We have the schematic substitutions are finite representations of infinite sequences of first order substitutions. I did something funny here in the second bullet point, right? We have the same thing syntactically, it has the hat symbol, but notice that our variable looks a bit funny. So this is not a first order variable. It can be. So if you look in the last bullet, that's a first order variable, all right? But we also have this concept of global variables, which are variables which take arguments as well. So we actually added an object level definition of indexing to the variables as well as term sequences. And this is something that becomes important. We'll see this in the examples. But both of these types of bindings, the ones with variables with indexing, the ones without, are allowed in our language. Right. Substitutions also normalize as you would expect them to normalize, just like they do with terms. You could normalize the term on the right-hand side of the substitution sign or the binding, or you could actually it shouldn't be or it's an and you could actually normalize the variable. But variable normalizations is quite simple because they just take parameters. So this is just really a syntactic representation of indexing. So let's finally get to define what it means to do unification of term schema. It's not so surprising at all. If you have these two term schema, S hat and T hat, right, we call them unifiable if for any parameter assignment, right, okay, so for any parameter assignment, this substitution here, lambda hat n, right, makes them equivalent. So this is essentially just saying that we are talking about unification of two infinite sequences of terms. All right, but finitely representable infinite sequences with a finitely representable substitution. Just everything. We have representation languages for all of these things, but we didn't want to complicate it in this talk. So depending on the types of variables allowed in this lambda hat n, all right, and S hat and a T hat, we could define two different types of unification problems. The simple term schema unification, where only first order variables are allowed, and the global term schema, where we also allow these global variables to occur. All right, so this is just something to keep in mind. All of our symbols that are defined are ordered to make sure we have primitive recursive definitions. This is the formal definition of a simple term schema. As you can see, it's a lot like a primitive recursive definition. Most of this text is not really too important to read through. I will just skip through it. It's just that imagine that you could have multiple defined symbols, they have defining equations, and they're ordered so that we have a least function symbol. All right, and some function symbols don't have to be ordered, but every single chain is ordered to have a least function symbol. I really have to get to the example which we have here. All right, so we have these defining equations for f hat, f1 hat, and we have g hat. All right, so I keep these colors consistent through the talk, so you'll see them again. All right, so note that we have to have this relationship between f hat 1 and f hat, that because you see f hat 1 calls f hat, so they have this relationship. The relationship with g is irrelevant, right? If we actually were to assign, we do some kind of normalization here and assign do the parameter assignment n to 2, we get this term on the bottom here, hx, hy, h of aa. All right? This is what we get from normalizing f1 hat. So let's look at some unification problems here. So let's take this first unification problem, which is f hat xn and g hat yn. All right, okay, so they have different variables on each side. All right, and for 0 and 1, it's pretty obvious that this is unifiable. All right, however, the infinite sequence is not, because if we look at 2, we find that on this second step of unification, we are guaranteed to have a recurse check failure. This is because of this variable repetition. So we're looking at infinite sequences of variable repetition. Okay, so it's always a finite number, but yeah, as n goes to infinity, this will eventually, the variables just we keep having more variables. Yeah, so I didn't expect this talk to be perfect. So a simple term schema unification, right? So we started this this is going back to this same topic, right? Sometimes they are unifiable. So let's look at a case when it is unifiable, right? So here we have the unification problem with f1 hat and g hat, all right? So if we evaluate at 2, all right, it turns out these are actually unifiable, all right? This is a really complicated looking term. What you're looking at here, right, is essentially the complete binary tree that's being constructed, right? We're just doing all of these, let's say we're doing all possible instantiations of h, a, a. This could actually be turned into a schematic unifier as well, which we give on the bottom. I couldn't come up with a better name other than MGUS. And it's what that follows down there. This is where we put x to g hat, f hat, f hat. And those are the two arguments. And then we have z just maps to f hat. And then we get this complete tree here. So this is an example of a problem which is unifiable. So some of them are unifiable, some of them are not, but a lot of the times you'll be affected by a recurse check, and this is just going to fail. All right? And now you can maybe see this recurse check problem is where we bring in the global variables. All right? So a recurse check failure happens in many cases. If we look at all the different combinations we could have made on with the previous defining equations, you'll notice there's a lot of recurse check failures. All right, so if we want to minimize them, we could look at how we treat these variable sequences, right? An easy case is when we look at the universal quantification, right? We can either quantify all of those variables as the same variable, so we just say for all x's are the same, or we could think about them as all being distinct. In a normal first order term that's not schematic, this last case is perfect, because then you could just define how the equality of variables would be yourself, and you don't have to worry. The schematic case is not so easy to do that. And that's the reason why we want to move the indexing to the object language, so that the schematic definitions could give you some idea, could somehow define how these variables are going to be equated. All right? So this allows us to syntactically describe properties of this quantifier prefix for these schematic length terms. And it reduces the unwanted recurse check. We don't really give an example of this in this talk, but this is the case. This is what in the paper there's more talk of this kind of examples, but here we just give one of the best looking examples for schematic terms that have global variables. This definition is pretty much exactly the same as the simple case, except for now we have these big X's, which are the global variables. Notice that the domain of the unifier, right, is dependent on a numeric parameter, right? We refer to these now because these are actually schematic substitutions. Both sides of the substitution are schematic now. And they could still have a finite domain, but as our example that we give here, we actually have a growing domain as the parameter increases. So let's look at these two definitions here, f hat and g hat. So this is very similar to what I had before. We have this, one of them is associated left and one of them is associated right, and we want to consider the unification here. And similar to this growing tree that we had before, we have the exact growing tree here, but we're doing a different instantiation at each x. So you have the a is being instantiated here, then we have x1 goes to h of AA, x2 goes to the next one, and so on and so forth. And we get the schematic unifier with growing number of bindings. As you see, the number of bindings is dependent on n here, where each xi just goes to h hat I. So notice, unlike the previous example, in this example, we had to introduce a new function symbol h hat. All right, in the previous example, we use g hat and f hat. But here we actually have to introduce this new symbol, and we have the defining equations here on the bottom to actually make this work. Now you see, the global variables add this extra complication to things. So, so we have these above definitions, right, which don't use the full power of primitive recursion because we're missing some important functions. So if you notice something, we don't have projections here, and we don't have constant functions. So this is just additional, so we could define our open problem, some interesting questions we have. We add this idea of projections and constant functions so that we actually have full primitive recursion. Our defining equations give us composition and give us the primitive recursive operator, so now it's complete, and we could do any primitive recursive function in this setting. So now to the open problems, almost done here. We could look at it when we have the simple standard schemata of recursion depth less than or equal to 1. Is this decidable? Well, we just have to reduce it to the equivalence problem of loop 1 programs. This hasn't been done yet. It seems like a tractable problem. All right. Same question comes up for the global standard schemata. Right. We're not really sure how to handle this. Probably similar to the first question. Right, but notice that the unifier's domain size may vary here. So this is getting a bit more complicated and technical, and it would be interesting to know this. But what's a bit weird is that when you remove the standard, right, it becomes possible that maybe we don't have to reduce the recursion depth to 1. Maybe for any recursion depth, because the recursion is so weak. There's not much you could do when you don't have the projections or constant functions. It really reduces the expressivity of the language. And the interesting thing is this actually shows up in the resolution calculus. So it's not like this is a bad idea to check this out. We conjecture that all three problems are decidable, but we haven't looked at them yet, and this is something for future work. And we just thought we'd share these ideas with the community. So to conclude here, term schemata provide an interesting unification problem motivated by computational analysis. So this is a computational proof analysis. It wouldn't have come out without it. Equational variance is always something that people ask us, and yes, we're interested in it, but it complicates the matter so much we haven't touched it yet. All right? We're also looking at probably existing unification problems which are close to this and maybe could help us out, such as term graph unification and higher order unification, though we doubt that higher order unification is going to help us out much here, but term graph possibly, especially term graph unification with narrowing. The notion of MGU is something that we know should be there, and we haven't worked it out, we haven't formalized it, and this is something that we're currently investigating because we don't really know how to put the unifiers in relation yet. And this is something that we are doing right now and will continue to investigate into the future. So this is the end of the talk. I guess stay on this slide, and I'm glad there was no interruption, so I won't have to do any cutting. I hope you enjoyed the talk and looking forward to the Q&A. Just come to it, please. Yep, so that's it.